So I'll do my best to be brief, precise, and not to speak too fast. It was brought to my attention that sometimes I tend to speak too fast. So I hope you can see my screen now. I can see that you can. So it's a pleasure to meet all of you. It's a wonderful auditorium and really a great event that you're organizing and hosting. So it is a pleasure to be here, to attend. Mentioned, I will try to introduce and speak a little bit about some of the latest technologies that are available and that are being used in different parts of the world to help with some emerging issues that we have with the increasing dynamics of the new grid. So with these power electronics enabled power systems, where we have a variety of different sources connected in different ways, on-grid, off-grid regimes, and what are the challenges that we are facing with these changes and how we are addressing them. So this is the short agenda for today's webinar. So this introduction is going to be very fast, just a couple of minutes, and then I'll focus more on some of the experiences that we came across when it comes to the new power systems. So about new challenges, some solutions that are proven to work, and I will share with you some of the experience of our customers. Then very briefly, I will introduce our company, who we are, how we started doing what we do. And then we'll go through a couple of demos. I will show you how some of our tools are working. Then we will have a special treat for all the attendees of the seminar. We are going to give special access to our software tools, special trial, if you may, for all attendees. Mr. Rados Petrovic, that is also there with you, is going to give you the credentials at the end that you can access our software, download free of charge, and share among your auditoriums and students to spread this technology a little bit. And that's it. And then finally, we can have a short questions and answer sessions if there are any questions at the end, and if the auditorium is awake at the end. So because this is in total 1.5 hours. So if needed, we can also make a short break, maybe between the presentation and demonstrations, a couple of minutes to stretch legs, and then we can continue to the demos. Also, I would encourage everyone to stop me at any point if there are some meaningful questions that you would like to discuss. Then we can also do that. So that's it. So I would start. So as mentioned, as you saw from the topic, so we are going to speak closely about protection, about new FEX devices, about distributed generation, hybrid systems, both terrestrial and offshore, and how all this is impacting our existing infrastructure of the grid. So here comes this title. The new grid is all about software, meaning that in difference to the old grid that we had for about a century, this good old Nikola Tesla invented transmission of electrical energy over long distances with zero losses. Nothing pretty much changed in the power systems until, let's say, 10 or 20 years ago, when we started adding these renewable sources to the grid, to different points of the grid, mostly the distribution layer. And then also these energy storage fields, where we now have combinations of conventional and alternative sources operating closely in some isolated parts of the grid. What happened here? Well, basically, all these converters that are connecting renewable sources or storage facilities to the grid are power electronics converters that are operated by some form of software. And then on top of this, we have communication layers, which are again new layers of software. So in difference to the old grid, we can say that now this grid is quite complex when it comes, because we added layers and layers of code and software to it. Similar things happened to automotive industries about 20 years ago. This is why now we have about 80 microprocessors in every car. What this means that wherever we have software, there are potential failures, potential bugs that can ruin the stability of our network, and all this software has to be tested. And the questions are how we can deal with these software issues, how we can test our software, how we can commission this software before we are actually letting it work in the real power system, in the real environment. So these are just some of the challenges that we are facing. It's nothing strange to say that performing tests on megawatt equipment in labs is not really such a pleasant thing to do. It doesn't scale easily. Our tests are not repeatable. We cannot automate the test processes. It's dangerous. It's endangering people's lives. So the question was whether there are some new technologies that can help us deal with these issues, that can help us bulletproof our equipment and harness the potential of software and complex control fully, so that all our life can be easier, so that we can scale up or multiply the number of operating points and tests that we can cover, so that we can bulletproof our equipment against particular grid codes. And this is it. So the question is whether we are having some tools that can help us test our equipment for any kind of disturbance, for any kind of fault, for any kind of shoot through, faulty switch, for anything, any scenario possible that we can think of before it actually happens. And of course, is it possible to automate these testing processes? You are probably all familiar with this big trend of let's say, new generation of grid codes that any distributed resource in the grid or that any protection device has to comply with or comply against. So these new emerging grid codes that are now also not, India is not also stranger to this form, especially with this need or this resolution of your government to install about 200 gigawatt of renewable sources within the next 7 years. All these sources will have to be tested against particular grid codes that are becoming more and more complex by day. We are speaking about tests like low voltage write-through, frequency write-through, anti-islanding operations. So all these tests are extremely hard to perform in labs, especially when we speak about megawatt labs. So the answer was to see whether there is some technology that can help us deal with all these issues. We are also speaking a lot with some of India's prestigious institutions like CPRI along these lines to see how this equipment is going to help include all these distributed generation to the Indian grid. So when we speak about some traditional methodologies, this is a very simplified presentation. We are all familiar with the different simulation tools that we are using on everyday basis. MATLAB probably being the one most common, most familiar, and the one that probably every single attendee now to this presentation has spent some time with. What was problem with simulation is that the results are not that true, because not only that we are simulating the power part, we are also simulating all the control software and all the control system, which makes our results not as real. On the other hand, it was very nice cost-wise. It was very easy to work in simulations because cost is low. You can simulate anything that can cross your mind. Just problem was the results were not that good. And on the other hand, we had tests in the full power labs, or for example, in some power hill configurations where we are not testing, we are not performing any kind of simulation. We are still using power. So we are testing equipment with full power. The problem here was, of course, it's extremely costly. It's dangerous. It's slow. We can cover maybe 5, 6, 10 operating points per day, not more than that. But of course, on the other hand, the results were very good because we were testing the real stuff with real power. But the question was, is there something in between that can provide us with great results, but also with some ease of use, something that can scale, something that doesn't include power, so that we can automate the testing processes, perform regression tests, etc. And the answer was yes. Now, with new technologies that we have, with new computational platforms that we have today, we are able to simulate the power to make a digital twin of a network or of a power stage of any kind, and simulate it in such a manner that the actual control system can be connected to the virtualized power stage. This means that we can now use very fast computational platforms to solve some very complex equations that are describing particular systems, and we can interface real control, real protection devices, real facts devices, all these smart layers, all these software layers of the network, and we can interface them to a completely digitalized power stage. This concept is now known as controller hill. How this looks, basically everything that has power is simulated with specialized computers, and then everything that is executing some form of control algorithms, being in protection devices or converter control, is being interfaced directly with these specialized simulators. If you want to see how this looks in real life, these are just some examples. What you can see on the left are some snapshots from labs in Schneider Electric and ABB. Schneider Electric also in Bangalore is probably one of the biggest customers or biggest users of this technology in India. So this is how it looks in real life. So actual control systems, actual protection devices, all of these can be connected to these kind of boxes that are then, we can call them even specialized computers or supercomputers designed to only do this, to simulate the behavior of power system entirely. So this is how it looks in real life. Now, this is of course only on the converter level. This is how the technology started, because if we speak about dynamics and comparing power systems dynamics to the, for example, converter level dynamics, we know that converters are switching on very high frequencies, which then demand very small simulation time steps on which this computer have to perform. So the biggest demand was exactly on the converter level. Then now we are expanding to the microgrid level and power system levels by adding some slower dynamics on top of this. So if we speak about the power system testing requirements to perform something like this, then we speak about a combination of different simulation platforms that are executing different parts of this model on different time steps. For example, for most of the power system simulation, we are completely happy with simulation time steps of, for example, 10 microsecond or maybe 20 microsecond, depends on the level of detail we need. But in order to connect real control of a genset, of a diesel generator, or of a solar inverter or an active filter, then we need to embed the real controllers. To connect them to this kind of simulation, these parts of the network that are being, let's say, controlled by real controllers have to be simulated in much smaller time step with much bigger dynamics. So some of the specs, if we speak about what would be the ideal test bed that could fulfill these kind of requirements, that can be used both for AC and DC distribution systems, that can let's say, perform on different execution rates, to also at the same time read PWM signals that are switching with, I don't know, 100 or 200 kilohertz for active filters, for example, and then also simulate another part to simulate a large network without overkilling our resources. and then also simulate communication protocols, synchronize with the GPS signals, embed real protection devices to the setup. These are some of the specs that this setup would have to comply with. So if you speak about timescales of interest in new power systems, we can see that now we have a really large span, starting from the microsecond level or even nanosecond level for sampling of the PWMs in the inverter switching. And then we go more and more to some hourly changes or daily changes when it comes to, I don't know, movements of sun or discharging the batteries, some shaded curves, fuel cell dynamics, and etc. So all of these time scales have to be, let's say, satisfied by the same very setup or same very test bed that we are using for our tests. And of course, just to briefly summarize what are the benefits, I'm not going to speak too much about this, and this slide speaks pretty much about itself. I mean, just to justify the need, why are we again searching for such alternative approach to dealing with our with the emerging issues of the new grid? Well, I mean, if we can avoid going to the lab by any chance and spending time with spending, you know, megawatts of power and kilowatts of power to perform some tests, this means high maintenance cost, high cost per operating point, very slow processes, and something that we cannot automate or perform well. So this is the idea. Now, this technology that we are speaking about has entered different fields. Not only the terrestrial microgrids and power system, power electronic applications are now depending on this technology. We see the great applications also with marine applications, some offshore platforms, so oil and gas, which is again energy. And then in transportation, where we have hybrid propulsions or traction applications, hybrid electric vehicles, microgrids of fast chargers, etc. So all of these fields are now being covered by or answered with the same technology that we are going to show more about later on. So just a couple of examples. This is one of the major heavy-duty hybrid vehicle manufacturers, Liebherr. This is a German company. So this is an example of application of such a technology for hybrid propulsion, combination of diesel and electric motors. Then one very interesting use case. Sometimes the most trivial things are the hardest one to deal with. So we recently had some experience with Statoil and Shell, who are, you know, pumping the gas, you know, or actually, let's say, transmitting the electrical energy from the very north of Europe to the south. Their biggest issue was that, you know, during the winter months, the transmission lines are going north-south and the wind is blowing east-west. And where we have strong wind, the lines get connected, they trip, and then the system needs weeks and even months to, let's say days and weeks to reboot and restart. So the greatest issue for them was to bulletproof the turbines so the whole system can reboot itself fast and automatically, so they don't have to send you know, experts to the field, spending tens of thousands of euros or hundreds of thousands of euros to reboot the system. So what you can see on the picture is the testing facility in ABB in Switzerland. Here on the picture, we have two LCI drives, 20 megawatt each, back to back, being tested, you know, in the lab. So this is the lab when they were testing the software that is driving these two machines. So 50 megawatt altogether to test software. So this was before they learned about the technology that they use today. So we were able to replace all this lab infrastructure with one of these boxes right here. So what you can see on these pictures is completely original control system that was driving this drive right here, now being tested on one of these boxes. So the completely 50 megawatt setup is simulated with this box, and then the original control system for the complete setup is tested here. So we're going to speak about more use cases later on. This is just to conclude this part of the presentation. What you can see on the picture also here is that this technology also found its place in the academic circles. This is one of the first hill-based teaching laboratories ever made by Professor Kushik Rajashekara, who is your countryman. Probably a lot of people there know Professor Raja. So he was one of the first to harness this technology for teaching purposes. What you can see here is a completely hill-based teaching facility that he established in 2012, so 5 years ago. Many more places like this now exist in the world because not only that this technology can help with actual tests, it is a very interesting tool and let's say easy to use tool, easy to spread when it comes to the teaching activities and research. So today Typhoon has aside from a growing number of let's say commercial businesses that are using this technology, we have also a very good relationship with a number of academic institutes worldwide, but also in India. We introduced ourselves in India for the first time, I think, last year. Since then, quite few academic institutes have joined or acquired this technology for their own internal purposes. These are just some, few of them. NIT Srinagar also ordered a couple of days ago one of their first hill units, NIT Uttarakhand, and more are coming, of course. So this is just a partial list. You can find actual testimonials on our website, sharing of different experiences, etc. Also very important for you as academics is that this technology is very well accepted by IEEE community. There is a growing list of papers published in the IEEE Explorer that you can find. There's more than 60 papers already published, developed solely and entirely in this environment that we are going to show in a couple of minutes. And just a few cases. This was one of the latest setups that we delivered to US Energy Department. What you can see here is a hybrid generation, so distributed generation test bed with let's say simulated network of let's say a couple of tens of buses, where we have different generators, different machines, some of them controlled externally, some of them simulated in some lower level of detail, active filter controller, the real one, connected to the setup, and some solar controllers connected to the setup. So this is one of the, let's say, most advanced microgrid test beds that exist in the world at the moment. Of course, it can be much larger in scale. This is just a short example. Yes, was that some question?
No, sir, there is no question. You can continue.
Okay, I thought I heard something. Okay, thank you very much. So just to describe what was in this particular test bed, these were some of the requirements specified by the US Department of Energy. So this is what was covered with this kind of setup. Of course, all this equipment can scale to very large applications depending on the need. Then active filters, something also that is very close to the protection, to the, let's say, the energy efficiency field. What you can see on the picture is active filter office of Schneider Electric in Oregon, USA. You know, it was very hard for people to believe at first that this technology can actually work. So what you can see here on the picture in the corner is how this commissioning process actually looks like. So, you know, detective filters are especially interesting, or they are especially demanding when it comes to the dynamics. So these are the converters that are switching on very high frequencies. So for people that are dealing with active filters, it's they kind of got used to doing everything in the little lab, you know, step by step, because there are not too many tools that can help them with what they do. So you can understand that there was a certain disbelief that this new technology can also work for them. So what you can see here is actually first attempt to connect the system, first trial. So this is why you see forest of wires when engineers were connecting, you know, line by line, piece by piece, and testing their control systems. Also another example, integration of 8 megawatt battery storage facility in South California, Edison. These, what you can see on the picture, are ABB control systems being tested on one of these boxes. This is also why this is very interesting for battery storage application, is that you know, batteries are probably the easiest to ruin during the tests. You just, you know, charge them a little bit over the limit, or you discharge them a little bit too much, then you ruin them, and they're extremely expensive. So for 8 megawatt grid battery facility, it was essential to simulate the batteries and validate the control without using actual batteries for this application. And etc. This is just also to show that more and more of the relevant facilities are accepting this technology, not only for testing today, but also as a part of the certification process. One of the first institutes that is pre-certifying the equipment against these very complex grid codes like BDW was AIT in Vienna, and now we are expecting that CPRI is going to be the first one in India that is going to certify renewable sources or these converters with this kind of technology that we have here today. So this was this introductory part, a little bit about the challenges, a little bit about what are the possible solutions, about new methodologies that we have today, as thanks to some enabling technologies from the market and some use cases. Then I will spend a couple of minutes just to present the company very briefly, so that you know who we are, what we do, and why are we doing this. And then we will switch to the demonstrations. Between these two parts, I would like to offer at least a 5-minute break, because paying attention for more than 45 minutes in a row is quite problematic. So after the presentation of the company, I suggest a 5-minute break, and then we can go to the demonstrations. So let's go through this part. As I mentioned, we are a relatively young company, started only, let's say, 9 years ago. But if we consider that the people who started the company were people in the field, spending years in ABB and some DMS companies, we can say that the need for this kind of tools, or the idea for this kind of products, emerged from the industrial needs much before this. So the director of our board is Mr. Rados. He's also the sole investor who backed our company. Probably this name would be familiar to you as a founder of the company Analog Devices. So a lot of you are familiar with the Analog Devices equipment. Yeah, and I can see that you're laughing to this picture of this building. This building is actually a donation from Ray Stata to MIT. This is Ray and Maria Stata Research Center. They donated the building to support the research activities of MIT. You can see that it's very unconventional design, to say the least. So 3 main offices of our company, one being in MIT in Massachusetts, and then 2 more, one in Baden in Switzerland. We also have an office in Technopark Zurich, and a strong development center in Novi Sad in Serbia, where most of our engineering takes part. So these are the founders, as I mentioned, but more importantly, I would say that people faces are not that important in this presentation. I would just want to mention that a couple of years ago, actually, sharply 2 years ago, this technology that we are speaking about was recognized by one of the international survey companies called Frost & Sullivan. There is a very interesting report that you can find on their website and also on ours about, comparing some of the different technologies on the market that are dealing with these issues. And that's it. A couple of years ago, the same team that started Typhoon Hill was awarded with the same prize for the medium voltage drive ACS 2000 that you are probably familiar with. So this is the founding team of Typhoon Hill. And then a little bit about the technology was covered in 3 different market research reports in 2015. I won't go too much in detail about this. So this is only for those of you who are interested to learn more about this field. All of this information is available on our website. So what is specific about our product offerings, something that was different before and after Typhoon Hill, our systems were the first one to be offered as a completely integrated package, meaning that all the hardware and software and all the tools that are needed to perform these kind of activities are coming from one company, not from multiple vendors, so through turnkey solutions. And then for those of you, this is probably the most common question that we are getting from time to time is which kind of tool is suiting for which kind of application. So this is just to show what are the most common applications where this technology found its place. Again, something that maybe is interesting only to a part of you to see what are the technology bottlenecks when it comes to different applications and which kind of system is best suiting for which kind of demand. So these kind of systems that we are speaking about can at the moment perform or let's say deal with networks that are let's say up to 1600 three-phase bus complex. So this is the maximum size of the grid that we can deal with at the moment. And that was this part. So before the demonstration, I would just like to point out a few useful links on our website that might be of interest. So let me just open the website. So a lot of this information and a lot of very nice recorded demos and different webinars are available on our website. I will just point a few links for those of you who are interested to learn more. So on the typhoonhill.com, you can find, for example, some nice recordings of this microgrid testbed that we were speaking about. So much more details about what is inside, how it's interfacing with protection devices. And here on this page, you can see even the link to the video recording of this setup that I was showing, how it works on large scale, how we are applying different disturbances, some transients, follow different things. So all of this is available on the website. So I'm not going to spend too much time or waste your time on this, since you can see this all yourself. Then another part that might be interesting for you is under this My Typhoon and then webinar section. Here you can find a number of recorded webinars about application of this technology in different fields, from grid code compliance like SunSpec, or pre-certification of smart inverters, some energy presentations coming from the military perspective in US, then et cetera. So you can find a lot of these webinars right here. And also, if you're interested to learn more about different experiences from different users, there is this area under company and customers where you can find some, let's say, first phase quotes, experiences, etc. about what this technology can do. If you are interested to learn more about this, so these are just some of the institutes that we are working with. You can download the complete list of published papers right here, or watch some additional tutorials, see how different schools worldwide are applying this technology. As I mentioned, a list of published papers. All of this is available on the website, so feel free to browse a little bit, download, or even ask some of these materials directly from us. We are happy to share them at any point. So before we continue, I would just like to add a comment to the statement that the software is free. It's not that the software is free. We are giving it away for free, meaning this is a significant part of our product when it comes to the commercial, let's say, accounts. But because for us, academic network is very important. We see academic institutes as strong partners in bringing new technologies to the field. This is why we want to use this opportunity to open this software to all your partners, to all your institutes, to all your students, free of cost, so they can get familiar with the technology, but more importantly, to influence the further development of the technology in the following time. So for us, this is a gesture of goodwill that we would like to encourage all of you to download this software, to play with it, to go through the examples. We have a local partner from Quarbs in Kanpur. Representative is right there with the madam, as madam mentioned. They can give you more direct coordinates how to download the software and use it. And then that's it. I will show you a little bit how all this works. And then if any questions you may have, we can discuss these things at the end. So share my screen. So what you can see now is the home screen of our software toolchain. So this is everything that I will do now, today, you will also be able to do yourself when you download the software. So I'm not going to show you anything other than what you can do. So for anything other complex things or anything that is requiring some piece of hardware, this won't be shown today. For this, you have a lot of demos available also on our website. So for me, it's more important to show you how you can start with this software, how you can start using this, how you can browse through examples. This is the highlight of the today's presentation. So what you will notice from the first moment you install and start this software is that it's very clean. We are doing our best to only add the things that make sense and that people are using. So this software and the hardware that is running along with it is made ground up for power applications. So you won't find anything else in this tool other than elements needed for power applications, whether these are power electronics, power systems, something applied to the marine applications, large system, small system, and everything you will find in here is made ground up for this application. If we are comparing to MATLAB, this is like MATLAB designed for power engineers. When I say this, this means that every element in the library on the left is designed for power electronics and power system engineers. What makes this approach so great or so easy to use is that modeling of networks does not require any deep understanding of any programming language. So designing circuits like this, what you can see here is IEEE defined 30-node feeder with some substations, some measurements on every bus, then some transformers, underground cables, transmission lines. What you will find first is that customization of this kind of model, of building this kind of model, requires only knowledge of electrical domain, meaning every model is parameterized by its technical spec. So 0 equations. So for the transmission line, you can choose which kind of model you like, whether it's RL coupled or PI, number of phases, 2, 3, 4, model definition, and etc. So nothing complex. You need some converter topology. This is how you model converters in Typhoon Hill. Just drag and drop them. That's it. If you want this converter to be controlled externally by a real controller, you just choose which control signal you want to use to drive which switch inside the converter. If you want to control it internally, then you say internal modulator, and then just define the switching frequency, that time, etc. So all the modeling, everything is done completely with your mouse. So no need for writing equations. And then this applies for anything that you can find in this library. Some usual libraries that you came across with in MATLAB, like this mathematical operators, discrete functions, custom C blocks, it's all here as well. Additionally, we have libraries of very specialized elements like different IEEE defined exciters, some steam turbines, governors, etc. So the library is very rich, I would say. It's also constantly growing. We have 4 updates of software every year. So major updates that are bringing some new models, some new features, etc. And all these updates are influenced and driven by the market. So when I said at the beginning that we invite you and encourage you to use this software and give us some feedback, this is what we mean. Feel free to join our groups on LinkedIn, on our website, our blogs, and write comments, suggest changes and updates, etc. This is as far as the library is concerned. When you download the software, you will also download the complete documentation with it. So if you are wondering what kind of element you can find in the library, there is this Typhoon Hill schematic editor library document that you can open and find this detailed description about everything in our system. Solver logic, hardware information, but also information about any model that is inside the library. For example, you are interested how a particular machine is implemented, you will find the equations of the machine, complete subsystems, and everything. So that's it. So I'm not going to go too much through the library because you can download this document yourself and see everything you're interested in inside here. And then the level of complexity of the system completely depends on you. Everything can be modeled with small detail if you don't need something specific, or you can go to very detailed models like, let's see. For example, this relay right here is modeled right now in our circuit, in our system. If you go in the layer beneath, you can see how this model with how this relay is implemented with 4 protection functions. Every one of these blocks you can go beneath and you can see how the actual logic of this system is implemented. But what is the most important part, I would say, of all, is that once you're done building these kind of models, compiling this and executing in the form of simulation is just one click away. So the system is going to recognize what kind of circuit you are building, how you are organizing the circuit, which Hill device, which hardware device you want to use at the end for this model, and it will compile for a particular hardware device from the scratch. Right now, we are set to use the smallest device that we have, this 402 Hill. This is the entry-level device that we have. And although we are going to run this model in offline regime, it's going to be compiled for a particular Hill device so that you can switch to real time just by plugging in the USB cable. Compilation lasts less than a minute. And then let's see what we are compiling. So we are compiling this IEEE defined 30-node feeder. We are going to run this model now in offline regime to see how this works and to see how accurate our models are. So this is one of the models that is defined by IEEE community to serve as a testing model to test and verify the accuracy of your simulation platform. So our models are in less than 1% error, which is quite precise. IEEE is allowing 5%. So the model is done. The system will automatically going to switch us to the next step called control panel, where we can set the sources, play with frequencies, change any parameter of the circuit, and do all this while the simulations are running. And then interfacing to the real hardware device, as I mentioned, is just plugging in the USB cable. So my PC is a bit slow, so don't mind this. So there we go. The model is done. What the software is asking you now is that it cannot find any hardware device connected to the PC. This is going to happen to you also because you don't have any Hill devices. So what it's offering is to load the model to the virtual device. This is an offline simulation mode where we are simulating the behavior of the Hill device on our PC processor. Again, this is completely hidden from the user. So if you noticed, we haven't done anything to, I don't know, to deal with the compilation process. It was completely automated, just one click and everything is here. The same compilation process is when you use hardware devices, it's completely the same. If you go back here and you take a look at the compiler log, you will see that this model, this whole network is going to run with a time step of 8 microseconds on the 402 device. And you can see how much of the 402 device resources would be utilized for this model. So let's go here. We can load the settings. Every example in our system comes with the predefined settings, which includes, I don't know, the setting of sources. So this is the grid voltage, the grid frequency, etc. And of course, every one of these models that we are running is coming with the UI file. This is like a user interface file that you can run to play with your models. So this is this one example, a very simple one, easily recognizable. Now, as a next step, I would also like to quickly show you how this looks on some different examples. For example, a battery storage inverter working in the grid connected mode. And in this example, we are going to run the converter with the control that we also designed in our system. And then we are going to start injecting some harmonics, injecting some different grid faults to the system. Just stop the simulation. And then play with this circuit for a while so that you can see what kind of tests can be performed easily. Finally, after this demo, I will going to show you another example of let's say, offshore microgrid. This is going to be a ship. You can see the propulsion of the ship here with the induction machine model, some different models of the load, etc. But first, this is the model that we are going to run now. This is a battery storage converter. So you can see here the battery model, again, that is coming as a part of the library. You can see that as all other models, this one is also customized only through the technical spec. So even for battery models, we have some predefined battery types, nominal voltages, etc. So this is how we are designing the curves of the battery. This converter is going to be controlled through internal modulator. Just a second for the model to load. So this converter is going to be controlled through internal modulator through this control algorithm. It's a closed loop control. And the switching frequency for this converter is going to be 10 kilohertz. So in order to run the model, And this is one of the examples that are coming with the installation of the software, so you can run it yourself. I'm just going to open the custom UI, meaning the interface file that you can also, again, design yourself. We have a built-in scope that we can use to observe the grid voltages and the currents of the converter. And then we can start playing with the system. For example, add harmonics to the network. Then you see how your converter is going to behave with a particular harmonics injected to the network. You can optimize the filters, etc. Switch back to the nominal grid, unbalance the grid. So any kind of test that you can think of can be easily executed, implemented here. On the back of every one of these buttons, if you double click, you will find Python code. So this is open source programming environment for those who are really advanced and would like to spend, to do some more advanced things here, like test automation and working on automated test scripts. This is all available here. Of course, all these harmonics changes, the unbalanced grid, all this can be done even manually. You don't have to build these kind of interfaces, although they are built quite easily. All of these operations can be performed again with your mouse click. For example, you want to simulate a broken switch inside the converter. There you go. One of the switches is now not conducting. And then you can see how this is influencing the grid, etc. So these are some simple examples, the most basic ones. When you download the software and you open the schematic editor and click open, you will find yourself in this folder. But you will find a lot of examples in power system domain, in power electronics domain, in microgrids, in hardware in the loop, meaning embedded external controllers that you can run from the scratch and play with. So if we open power electronics, you can see this battery storage example that we are running right now. There are some simpler ones like boost closed loop, and then some induction machine, open loop, etc. So feel free to experiment. Feel free to browse through the examples, play with the software, join our LinkedIn group, and see how useful or not useful you find this in your regular teaching activities. Then one more example that I would like to show you is this marine example. So this is, as I said, a power stage of a ship where we have some diesel generator, some generator measurements that we have right here. So power measurement layer, propulsion with induction machine that is connected to the machine shipboard through the three-phase inverter that we are again controlling with the control algorithm designed in the same environment. Here we have some battery storage facility that is again controlled internally, and then some auxiliary loads here. So the complete shipboard power management system that again can run, this kind of model can run even on our entry-level devices with a very small time step. Again, compiling this model and running is just one click of a button, and you will see now the compiler log compiling this model for the HIL 402 for an entry-level device. So what you will get from our partners right there, from Mr. Rados Petrovic, who is sitting with Madam right now, until this model compiles, I can show you where you can download the software. Just open the browser. So if we again go to our website, there is a part on the right called My Typhoon. Then there is a place where you can, where it says login. So when you go to login, you are immediately transferred to the subscription page. I will log out so you can see how this works. So you're going to find yourself on a window like this. Then you can sign up right here and use activation key to register that Mr. Rados Moria is going to provide you with. So this is going to be a fully blown software environment with all the toolboxes and everything included to your license. So it's not just a free trial copy, it's a full-blown software that you can use. So the model is almost done. While we are waiting for the model, if you have any questions, feel free to ask also now. There we go. So the complete ship power stage is going to again run with the time step of 1 microsecond, even on our smallest device, on this 402. Just for the comparison purposes, for those of you who are dealing in power systems, our entry-level devices, this KIL 402, can simulate roughly a network of 83 phase buses with all the loads and switches and everything, with time step of 10 microseconds. The simulation was running, so this is why. Okay, I'll load new model. There we go. So there we go. Now we are in the shipboard power management system, running the simulations. You can start the propulsion. You can see the power. You can go to the layers below. This is a battery storage measurement facility, generator facility. So all of these propulsion facility and all the measurements. And here command to start and stop the propulsion in this custom UI that we build ourselves. Again, the scope is there. You can choose which signal you want to observe on which channel of the scope, and all these advanced functions that you would have on any other scope, like observing digital signals or capturing. Let's say we want to capture all this data that we are dealing with. We can force the trigger. Say we captured all the signals. We can zoom in to really large detail. This is 2 megapoint capture function, so that we can export to some, let's say, to MATLAB or some other software that you would like to use for some kind of analysis. So all this is inside. So I wouldn't go in too much detail. I would prefer to make it more of a discussion now. So I'm opening the stage for any questions that you may have, because all this software and all these examples are going to be completely open to you. Just download the software, use the activation key that will be given to you by Mr. Rados Moria. And then we invite you to share your feedback, and that's it. Thank you very much for your time, and please do ask anything that you have on your mind.